Hello, everyone. I'm Saibdeep Singh with my partner Bhavith, and we'll be walking through traffic light simulation for urban vehicle management. So today we're excited to walk you through our project focused on how traffic flows on one of the busiest intersections in New York City, Fifth Ave and 42nd Street in Midtown Manhattan. It's a high congestion zone, as we all know, with all kinds of vehicles moving through cars, trucks, buses, bikes, e-bikes, especially during peak hours. We use a platform called AnyLogic to simulate this intersection and study how things like signal timing, vehicle type, and entry rate affect traffic performance. Our goal was to create a realistic model using real New York City data and explore how different traffic setups impact congestion and delays. Now, backing up a little bit and just moving into the introduction, as we all know, New York City is known for its heavy traffic, and Midtown is one of the toughest areas to manage. We chose to simulate a real intersection to better understand what causes congestion, especially when you mix different types of vehicles like buses, trucks, and cars at a fixed signal system, sorry. Simulations give us a way to analyze things like traffic buildup, wait times, and signal impact, all without touching anything in the real world. It's a safe and flexible way to test possible solutions and see what works best in these congestion zones. Now to move into the background and research. To build something realistic, we started with just a little bit of a foundation, right? So we pulled traffic data from NYC DOT, MTA ridership stats, and NYC's open data portal. This helped us actually understand different traffic patterns, like how often vehicles enter intersections and how long they wait. We picked this intersection because it's where major traffic flows meet, right? So with a constant mix of private cars, delivery trucks, and public buses. This data helped us fine-tune our simulation from vehicle mix to entry rates to signal delays. So it closely really reflects what really happens on the New York City streets, especially the ones with high congestion zones. Now passing it on to Bhavith to walk us through a little bit of our model.
All right, so going into the model overview and flow, this slide mainly shows us the traffic flow structure that we used in our simulation. So going into any logic, every vehicle moves through a cycle that includes a source, a move to, a delay, and a sync. Each part of this represents a real-world step in a vehicle's journey through an intersection. So for the first part, our source, that's pretty much where our vehicles are generated. So these represent the entry points like a bus turning on to Fifth Avenue or a car arriving at a light. Then we have our move to, which really defines the path that the vehicle follows. So it reflects the lane choice, the vehicle speed, and how the vehicle interacts in space. Then we have our delay, which is our critical piece. It represents the red light. So a vehicle stops here for a predefined amount of time before continuing, and that's where our queuing begins. And then finally, we have our sync, which is the exit point. So once the vehicle passes through the intersection, it exits the system. So we modeled different vehicle types. Obviously, we have the cars, trucks, buses, you have bikes. Each of these follows this path, but we have slightly different behaviors with each mode of transportation. And this system pretty much lets us simulate real traffic behavior and test how long queues form, how quickly roads clear, and what happens when traffic increases. And just moving on to that. Moving into our project structure. Here you guys could see our components and how we arrange them in any logic. So we could see that we have a modular design. Pretty much means that each part of this model, like the vehicle flows, signal logic, or lane movement, is built in as a separate component. This allowed us to make changes easily. For example, we could increase the truck entry point or change the timing of one specific signal without affecting the entire system. We also separated flows from four different directions. So this means that Fifth Avenue and 42nd Street could have a different vehicle input, different signal delays, and different congestion patterns, just like they do in real life. And one more thing we wanted to make sure of, not in just this project, but if we want to work on this project maybe long term or go more in depth, it's that we could add more intersections, add more pedestrian signals, or even add more sensors to make it like a live adaptive model. So it's very flexible and adaptable. and can be, expanded on over and over again. So moving on to the model description, this is pretty much a recap of the high level where the software we use any logic. Entities we have bikes, cars, buses, trucks. Our different blocks are source, move to, delay, and sync. And again, we have 3D models that you will see in the simulation that will be incorporated. So moving on to, the model description, even more continued. So the model was validated again through NYC studies, DOT traffic volumes and whatnot. Vehicle entry rates, delays, flows patterns were also calibrated to have real world behavior compared to Fifth Avenue and 42nd Street. Obviously, we ran multiple simulations, and results will show realistic congestion and queuing patterns that will be found in the Fifth Avenue and 42nd Street in real life. So moving into our validation and experimental design, in terms of technical design, we used AnyLogic's agent-based modeling framework. So each vehicle is treated as an individual agent with its own properties, such as speed and behavior. For example, buses move more slowly, so they stay longer at light, while cars move more faster and they occupy less space. In the simulation, you will see we have 3D vehicles for visuals for realism and easier analysis. And moving on to our results slide, I just wanted to get into how when vehicle entry rates were increased by 30%, our average system delay rose by 40%. This just shows how sensitive city traffic is to small changes in volume. We also found that buses and trucks caused the most congestion, not necessarily because they were slower, but because they blocked more space and took longer to clear intersections. We noticed that when both directions had equal signal time, traffic backed up on 42nd Street than on Fifth Avenue. This tells us that equal timing doesn't always mean a balanced flow, that some streets may need priority based on volume. And right here, we'll go into a simulation recording that we have, as you guys can see. As you guys can see, we're moving into our designated area, Fifth Avenue, 42nd Street. And moving into our conclusion and future work, I'll pass it back on to Sahib.
Perfect. Thank you, Bhavith. Yeah, I mean, just to sum it up, simulation helped us test traffic setups without changing anything in real life, obviously, right? So using real New York City data made the model accurate and useful, and using Fifth Avenue, 42nd Street, we just really saw in real time the kind of streets that we're used to in New York City. It's flexible, right? As Bhavit talked about, so we can build on it, add features, test other streets, or use live data in the future, right? So next, we'd really just love to expand this to more intersections and try out ideas like adaptive signals or modeling things like rideshare zones and maybe even event traffic, right? And yeah, that concludes our presentation. If you guys have any questions, please feel free to ask. These are some of the sources we used, and thank you.
Thank you, everyone.